Uh, I didn't plan to include this part, so this will be sort of digression. But during the break, I got lots of questions related to this, so I thought that I probably should include it. And also, this is intermezzo, digression, remarks, not in a mathematical sense, but just like sometimes I ask you guys questions, so maybe that's another one. How many of you like QFT or not scared of QFT? Like, no, not topology. And anyway, can't go down. Okay, so those of you who do like QFT, this is a sort of useful comment or set of comments that I'm gonna describe. It addresses where on earth what I'm telling you came from. I was planning to completely skip that, focus on math, theorems, definitions, properties, and so on. So this is gonna be like discourse in QFT. Those of you who didn't raise your hand, you have my full legal permission to completely tune off for the next 20 minutes and do something else, and I'm not joking. Or if you're listening, you can treat this material as lots of jargon that you can try on your family members, loved ones, or not loved ones, I don't know. If you want to scare people, so that's going to be a lot of jargon. So it's like QFT remarks, historical remarks, and actually, there is another point. The reason I'm doing this, it also is connections to other lectures, other lecture courses. So, yeah, I didn't plan to mention word transassignments at all in my series. And definitely not words like perturbative, non-perturbative. But since they came up, that's the reason I thought I would throw this in. And in fact, I did suspect there could be some connections to other lectures. I didn't realize that the opportunity is greater than I thought. So that's another reason of doing it. And I'm actually very grateful to be part of the team of lecturers. So I think it's a good fit. So anyway, next, therefore, 20 or so minutes is like digression. Then I promise we'll come back to rigorous math. I want to continue with theorems and we'll do proper things. So this is entertainment, but it's end of the day, so I think it's all pretty. So there is a thing that physicists call 3D correspondence. So I'll tell you a little bit about that. And this is kind of where something that I'm telling you came from. And it involves two sides, each of which is three-dimensional. And it's always a confusion, even among practitioners of this subject, on which side you're working on, because you cannot say, I mean, they're all three-dimensional. So it's always a confusion. And what it does, it takes a three-manifold, let's say M3, and associates to it a three-dimensional supersymmetric. This is how physicists write these things. Quantum field theory, supersymmetric, and there are different types of supersymmetry. So more jargon is that there is so-called n equals 2, whatever it is, quantum field theory. So this is not topological. It's an honest quantum field theory with all its richness, and as a result, we don't have mathematical definition for anything here, or well, for a tiny little bit, but not really. So it has a name. It's usually called T of M3. And this notation indicates that it's a set of theories labeled by three manifolds. So you give me a three manifold, for example, 3 torus, S1 cross S2, S1 cross genus 50 surface, there's gonna be a theory for it. So that's the story. So that's the correspondence. Okay? So in this correspondence, there are sort of two sides or two perspectives. There is a perspective of this 3D n equals 2 theory. So that's one side. And in this context, you can consider various partition functions, various observables. And what's relevant to us is so-called 3D, 2D elliptic genus, which is a generalization of elliptic genus for two-dimensional theories to this context, which involves two-dimensional something, I'll explain this in a second, and three-dimensional theory. So elliptic genus for physicists requires supersymmetry. That's why this sign has to be supersymmetric and so on. And this is something that we introduced back in 2013 with Puget Gada, Pavel Futrov. And again, I'll explain what that is and what kind of problem it solves. So this was important for development of the subject. So this is also called half index of the same theory T of M3. Or equivalently, it's a partition function of the theory on solid torus, which I'll illustrate like this. So it's a field solid torus. It's not a three-manifold. It's you take a theory associated to a three-manifold and put this theory on solid torus, which is itself a three-manifold. So that's again part of the confusion of this 3D. And what sits in the bulk is exactly this theory. So that's the kind of bulk part. But then because solid torus has a boundary, you have to specify a boundary condition. And here on the boundary, you put a 2D called 0, 2 boundary condition. I'll call it just B. And if this, so this partition function, so what I'm drawing is sometimes in literature denoted as 1 cross D2, but with the parameter Q here. Because if Q is exponential of 2 pi I tau, and tau is a complex structure on this boundary torus, then this partition function actually computes elliptic genus of this two-dimensional theory on the boundary if there is nothing in the bulk. So if for some reason this is completely empty, this is absent, it would produce for you usual elliptic genus. And I guess I can ask how many of you like elliptic genera or used or heard about elliptic genus? A couple of people. So, yeah. So elliptic genus is actually a very cool thing. And one way to generalize the story I'm telling you would be to take everything I'm saying and put a head of generalization of topological modular forms from elliptic genus and ask, okay, what happens there? So that would lead to a very rich kind of story. We're not going to go in that direction. But in any case, this is coupled 2D, 3D system. It's pretty complicated. That's why it sort of waited until 2013 to be discovered. And I'll tell you what things we try, why it didn't work. Because it requires sort of coupling of this two-dimensional theory on a boundary of this solid torus to three-dimensional theory in the bulk of this solid torus, computing this partition function, which in many ways behaves like elliptic genus. But even without going too far into physics of it, you can actually see something. So usual elliptic genus has nice modular properties. Again, if you have never heard of elliptic genus, this is one of the main properties. Here, you can suspect that there will be no nice modular properties as long as this three-dimensional n=2 theory in the bulk is non-trivial, because then it breaks SL2C symmetry of the picture. So one of the cycles is filled in. It's a solid torus. It's not a hollow torus. If it happens to be hollow, if there is nothing inside, then of course it's modular. So in fact, you can use this physics mumbo jumbo to predict in which situations you should expect nicer or worser modularity properties. So that's a good, useful perspective. Anyway, I'm gonna leave this for now. So this correspondence relates partition function on the solid torus. That's what we're talking about. So our z hat of q is basically this partition function. It's counting something. I'll come back to it in a second. But it relates this object to the other side. So from the viewpoint of our three manifold, this is expected to provide non-perturbative completion to complex Chern-Simons theory, or analytically continued Chern-Simons theory. In the Chern-Simons theory, where the gauge group is complex valued. And what is the issue? The issue, in fact, that appears in many other QFTs is that we're trying to formulate some kind of path integral, which mathematically is maybe not so well defined, of exponential of 2 pi I times some constant k, that's the same k we're using, times Chern-Simons of A. And suppose your gauge group is complex valued, then the space of the fields is highly non-compact. For instance, in Chern-Simons theory with compact gauge groups such as SQ2, space of flat connections is a compact manifold. It may be badly singular, but because holonomies take values in a compact group, you guarantee that there are no infinities in the space. But if your group is SL2C, which is actually what we are considering, then your space of flat connections or even non-flat connections will have huge infinities, and the main question is how to deal with that. So let me draw a picture, for example, for a space of either flat or not flat connections for complex groups on a three manifold. Here is a cartoon. It's going to be a huge space, but the important point is there are infinities. And mathematically, when we try to define something, we have to say how things regularize. So what we mean by this is, what exactly do we do with these infinities? Do we cut them off? Do we add some kind of divisor at infinity? So let me draw this divisor. And the story is that perturbative Chern-Simons on general three manifold was fairly well studied in, for example, early 2000s. So there is a fairly good control on what we mean by perturbative Chern-Simons on a three manifold M3 with complex gauge group. And here is the first time I write parameter H bar. So far I used Q. But here is the first time I write H bar, and that's the same H bar that appeared in all three other lectures except mine. So this is first time I'm adopting to everybody else and using. So we know how to compute this. In fact, this is labeled by choice of flat connection. So Konstantin called it A0. I'm going to call it alpha. So for each choice of alpha belongs in sort of that modular space. One can try to compute this, and this has been done. There is some control over it. But question in old days was, how do you package into non-perturbative Chern-Simons? So morally, what you want to do, you want to sum over alpha of all these contributions, z perturbative alpha of M3 H bar. Okay, so. And you want to take the sum in the sense that what you get is a TQFT. So first of all, you want to achieve invariance, make it three manifold invariant, and better yet that it's behaving sort of reasonably undercutting the blue. So that was the big challenge. And the issue back in early 2000s was that in many attempts to do it, it didn't satisfy some of the expected properties. So in the sum, what you want to have, so this is on my previous board, you want to have a contribution of all complex flat connections. And in some attempts, for example, I spent a lot of time working on approach to this complex transassignments using triangulations and so on. 1 billion flat connections were missing. So you get some kind of object which looks like a sum of these things, but it didn't include 1 billion flat connections. And that's pretty bad because every three manifold has 1 billion flat connections. So we cannot get away from this. Also, the goal to build this was to find something functorial that hopefully extends to 4 manifolds and so on. And there is no way to expect functoriality if you're missing some flat connection. So that was pretty bad. So the question was how to find the sum of package coefficients. So this was one issue. Related issue, it's not actually different, but it appears separately, is that there was great success in building combinations like this for open manifolds with boundary, for example, not complements or link complements. If you have S3 minus the link, very much like what we used as building blocks for cutting and gluing for surgeries, there was a difficulty capping it off, basically attaching solid torus. Again, that's different from that solid torus. Now we are on three side of the story. And it was very difficult to kind of go from open 3 manifolds to closed 3 manifolds. So that was a big challenge. How do we deal with closed? So this problem showed up in many, many different contexts. And for example, one is where in mathematical story of Fock and Goncharov, if you study various objects associated to surfaces, in their theory, it was crucial, for instance, to have one puncture. So you couldn't work with a completely closed Riemann surface, at least in original form. And this is exactly the same issue. Here, you could try to glue things as much as possible, but you still were required to have at least one cusp in this string manifold. So you couldn't basically patch everything up to make a closed object like a 3-sphere, Poincare sphere, the kind of things that we're discussing right now. So this has been going on for years and years in early 2000s. And people were expecting that there should be basically something like a function of Q, which, I don't know, is given by the sum. And many of us were looking for this function. So in a Q plane, we were basically trying to construct a function of Q, which has all the desired properties. And indeed, I was planning to draw exactly the same picture that Konstantin already showed you, that near Q equals 1, if we take this Q series and re-expand it in H bar, it would reproduce the perturbative sum exactly in this form. But again, this was difficult, this was kind of challenging, things didn't work out, and it wasn't clear where the problem was. So from one perspective, it looked like it's the issue of gluing because we couldn't get rid of all the boundaries. From the other perspective, it seemed like some flat connections are missing. So what's going on? So surprise, and that's why it took so long, is that there is not a single function, but a collection of functions labeled by the spin C structures. So that's conceptually what came from all of this kind of digression or historical discourse that I'm reviewing here. That and actually, the reason this carries ahead is because there are several attempts, and modified version had to be denoted with a hat, and it kind of reflects the process of like slow discovery of this. But the important point is that it's not a single function. It's a collection of things labeled by Q or by B, which is a spin C structure, which actually fits the bill and satisfies this property. So first of all, we can cap everything off, form a TQFT-like structure, so it actually behaves as TQFT and allows to deal with closed manifold. And also it includes contribution of all flat connections. So what the objects I'm telling you about morally, and actually not quite morally, but physicists would literally say that, it is exactly this resummation of perturbative contributions in something one would call non-perturbative. So I'm gonna write it down. So this would be precisely this fellow, ZB of NQ. It's kind of sum. An important point is, what are these coefficients, M alpha? So this is highly non-trivial. So in some sense, what I'm telling you contains the data of perturbative transassignments and the specific weights, the integer coefficients that you have to use to sum them up. Yes.
Where is B show up on the right hand side versus dependence on B?
Yeah, so that's a very good question, and that's why when I first saw this version of the story, I didn't believe it, to be honest, because to me it was a big shock. I spent like 10 years in early 2000s trying to make work what I just described, and it was a shock because there is no spin structure anywhere here. So I didn't expect Chern-Simons theory with complex gauge groups to depend on spin structures. So it's extremely strange that, first of all, we need this additional data and so on. So to answer this question, I have to dive a little deeper into nature of these coefficients. So these are called trans-series coefficients. And by the way, the technology that makes the statement precise these days often goes by the name of resurgent analysis, or resurgence, as some people like to call it. So it's in the structure of these invariants, which again were not accessible to us in older days, just thinking about perturbative invariants. So maybe another take on it is that you can take the story that I'm telling you and re-expand it near q equals 1. And the only novelty compared to something expected or traditional is sitting in this coefficients. So interesting mathematical question is, what are these invariants? How do they, behave, detect various structures and so on and so forth. If I have time, I'll try to say more about them. Again, I didn't plan to, but this may be sort of.
Yeah. Sorry, I might have zoned out for this. What type of thing was M alpha?
M alpha is a coefficient. A priori, it's a number. Actually, it is an integer number. But I have to maybe say a little bit more. Yeah, I think it fits in like this regression discourse. So to make this relation more precise, one needs a little bit more. In Chern-Simons theory, space of all connections, not the flat connection, this moduli space that I'm drawing, but all connections is not simply connected. So this is an important fact. This has to do with the fact that Chern-Simons of anything is basically circle value. So it's R mod, or even in complex theory, it's complex numbers mod integers. Okay. So therefore, when we work with Chern-Simons theory, we have to be careful. And besides specifying flat connection alpha, you often have to specify what's called integral lift. So therefore, I'll denote alpha the way I did, but one can also introduce notation where there is this boldface alpha, which lives in space of flat connections on a 3-manifold times integers. So there is this additional integer which reflects the integral lift on. So think about universal cover of your non-simply connected space. So this is an important fact about Chern-Simons. Those who work with Chern-Simons, of course, know this well and should know, but it is this integral lift that's important. Now, let me factor out, since this was already introduced before in other lectures, I'm not going to include this so-called classical term into Z perturbative. So then what will happen is that here, in this expansion, I'll have e to the 2 pi I k times Chern-Simons of alpha. But now, if I'm actually honest and trying to make this as precise as possible, this should be sum over this bold or kind of petty alpha. And what it reflects is that if this integer, for example, integer lift is n, I'll have here Chern-Simons of the usual flat connection plus some n. Okay. So now, in comparison to other lectures and various other notations, if k is integer, then having this integral lifts or not is not a big deal because integer times 2 pi I is still multiple of 2 pi I. It makes no difference. But the whole point is that if k is a generic number, and the way k is related to everything else is by q equals exponential of what I call the power is e to the 2 pi I divided by k. So then to make generic q, we want to make k generic complex number, roughly speaking. So therefore, if k is generic complex number, these integral lifts actually do matter. And what appears here, this combination, e to the 2 pi I times k, where k is a numerator, not denominator. This is not q. This is something that's often denoted q tilde. So therefore, what we can write is q tilde to this power. And and then this relation is actually correct. This is what people in resurgence study in detail. But then there are lots of coefficients. So this depends. So this boldface alpha is alpha comma n. And for some choices of n at 0, for some non-zero. So these are various integer numbers. So this is very full, important data of three-manifolds and how everything is packed. Again, I wasn't planning to talk about it. I think it does connect nicely to a lot of perturbative things. And since I mentioned sometimes problems, an obvious problem that came to my mind, in particular listening to Konstantin's lecture, is that one should try to connect H-bar expansion of the Z-hat object to BV quantization of perturbative complex transaminds. Because now we have tools for everything. I'm going to tell you more about what's happening inside unit disk. We can take the limit, re-expand, and compare to technology formalism that's being developed in parallel lectures. So those of you listening to both sets of lectures, that's a natural problem. It's a research problem. It's not an easy homework, but I think we have all the tools developed.
Could I ask you a quick question? So the alpha is sort of run over this flat moduli space, the moduli space of flat connections. So are you thinking of an integral over that space when you write the sum, or is it a summing over the types of connections that you have, or like?
Right, so this is a very good question. In fact, if they're isolated, then there is not a big deal. But actually, even then, things matter a lot. So that's why I was asking Konstantin this question. So it's extremely sensitive, even if they're isolated, to what's the stabilizer of the connection. So that, again, enters in a very crucial way. Then if some components here have positive dimension, then that's a further kind of ramification. So yes, it should be an integral, but there is actually more to the story. And if I have time, I'll explain it. Probably not. So then I'll just refer to this. I mean, I encourage people to look at this resurgent literature. I do want to point out one surprise. So again, this was 20-something minute digression. Hopefully, those of you who don't care about QFT closed your ears well enough not to listen, because we'll go back to something more serious. But there is sometimes physicists tell us useful lessons. For instance, at this time, it's still unknown as mathematical theorem whether Donaldson invariants are equal to Seibert-Witt invariants. So this is a kind of statement that comes from physics. To them, it's very natural. It's some kind of duality. But for us, it's extremely hard to prove. So physics sometimes provides useful clues, which even though we cannot prove, it's good to keep in mind as a guidance. So I already mentioned one such clue that even if we don't understand what on earth this picture means, we can suspect that if manifold is highly non-trivial, meaning that this theory is highly non-trivial, probably there's going to be no modularity property, or at least not in a traditional form like for elliptic chains. And that actually is true. Another prediction from all of this is that this physics picture provides some kind of embedding of complex transaminds in a much bigger story that involves fibrates, M theory, some six-dimensional theory. Six-dimensional because if you take 3 plus 3, you get 6. So it's actually strictly bigger than naive perturbative complex transaminds. And what happens is that you may suspect then that by doing this, embedding it in a bigger story and adding such compactification divisors, again, I actually don't know what's happening in actual physics, we do introduce additional critical points. So in other words, previously in old days, we saw that not all flat connections appear in this packaging device in early attempts. So now what may happen is that in the story I'm telling you, with this object, even more things will appear, more than usual critical points of complex transassignments. Until last year, or sorry, 2 years ago, there was no such example. So this was computed under by resurgence. It was related to perturbative expansions and so on. And there was absolutely no indication that there should be such additional critical points at infinity. But more recently, they appear more and more often. And that's, again, not surprising because this is embedding, it's like non-perturbative completion. We're taking simpler theory, embedding it in a bigger one, and that may bring more solutions to the table. Again, morally coming from infinity because our original space was non-compact. So that's what's happening. Okay, any questions about this part? So this was digression. It's end of the day, so maybe it was not an ideal choice to do it at the end of the day.
If you had to like recommend one resource for a mathematician that wanted to learn about resurgence.
There are many good sources actually. So Kansevich has a whole series of lectures. So in the recent years, he's actually obsessed with this subject. So he has lectures on exponential integrals, and well, this is exponential integrals. that's why. But there are many more. So I highly recommend many lectures and papers by, for example, Adidu Kostin. So David Sazan. And others. So these are analysts. As name suggests, it's analysis. It's a particular branch of complex analysis, which morally deals with the following question. So you have your domain of expansion, which may have some finite or zero radius of convergence of your function, and you want to expand the domain of expansion, or domain of where it's defined. And that's what resurgence analysis does. If I have a couple of minutes tomorrow, or we can gather for lunch, I can explain what it is. It's actually a pretty cool thing. It's very concrete, hands-on. It has some categorical aspects, but it also has very easy to learn computational aspects. And in that sense, it's not surprising because everything I have been writing and will be writing is expansion near Q equals 0. That's what we mean when we start writing Q series. We mean that each next term is smaller than the previous one. But expansion, as Konstantin pointed out strongly, that perturbative transassignments is near Q equals H bar near 1, right? So that's where we do. So that's why it's not surprising that this area enters. And again, these are some, I wouldn't say founding fathers. Founding fathers are generation older, but these are like active practitioners who made strong advances. And again, I'm not an expert actually on that area, so I encourage looking at. I'm talking to analysts in your department. Yes.
So should I understand this spin C structure as like describing a polarization for a quantization?
To your other question that you asked me in the break about GSO and orbifold, I said yes, because that's what it was. Here I'm not so quick to see if it's related to choice of polarization of anything. Again, I don't know. To me, it's a strange anomaly kind of thing. That's what physicists usually call anomalies. That you start working with a theory, it looks like everything is good, but then something is not as good and requires modifications and so on. So to me, that's what happened in this complex transassignment story. It started as purely bosonic, no need to know about fermions or spin bundles or anything. And suddenly claim is that non-perturbative definition, so it's not non-perturbative anomaly, whatever it is, requires this spin structure. Honestly, I don't understand it well enough in physics language. I can describe it from very different perspective, but it's probably not gonna answer your question. So I apologize. So there are many aspects in the story which by now people accept it, but I think they should be understood better. Probably this is one. Okay. Any other questions? All right, so then I'll erase this and we can go back safely to something very concrete, simpler. So this was a digression, jumping. The things that we want to do. So instead, let's focus on a simple lemma. So we saw that I gave you a definition of this object, which by now I can figuratively call non-perturbative completion of this complex transassignments, but it has its own meaning, it's its own life. And simple lemma, which is a good exercise, is that what I told you is not really an integral. So I gave you a much more complicated form that it had to be. So an equivalent definition of this Q-series invariant is the following. You can think about analogy with lattice models. So people who, I mean, in mathematical sense. So people who study lattice models, they have sometimes a lattice, which could be a square lattice, but we have a graph. So think about graph such that your spin variables will be sitting at vertices of the graph. So at each vertex, there is some spin variable ni. And in usual like Ising model, which is simplest possible lattice model, this ni takes values plus or minus 1. So that's why it's like spin or qubit, whatever it is. For us, this ni's will be a priori integers. And this actually reflects the fact that it is kind of like, yeah, so it reflects same infinity from complex transassignment. So the fact that this will be completely unbounded integer. So you can think of it as a model, lattice model, with integer spin, which has no bound. It's not just plus minus 1, but you're summing over all integers. And the question is how to make it defined. So given a manifold or equivalently graph in our presentation, we can say that, so this is definition, so I'll say define, as sum over all possible values of such n's assigned, so n is assigned to every lattice point. So this is very similar to lattice model. Then there will be q to the Hamiltonian, which is function of all these values of n, some function of ni's. And there will be a prefactor, product over I in vertices of some weights fi, comma, ni, which is a function I'm going to define in a second. It's local defined for one vertex, and then we just take product over all possible vertices. So you can try to move this factor inside this statistical weight or Hamiltonian, or you can treat it as a prefactor. That's not a big deal. So the Hamiltonian here is easy to describe. So this is basically minus a half, or some other coefficients, sum over I and j, ni, nj, b inverse ij. So B is our good old friend, that's connectivity or adjacency matrix of the graph. And B itself is very sparse. So remember that B had non-zero entries only on the diagonal or when vertices are connected. So such matrices are usually called sparse. But it's a standard fact that inverse of a sparse matrix is very non-sparse. In fact, we already saw this earlier in demonstration on a computer, where inverting this matrix produces something whose entries are very highly populated. So this is actually another difference from traditional lattice models. Not only we're allowing spin to be infinite in some sense because it has infinitely many values, we're actually talking about highly non-local Q of t, if you wish, on a 3-manifold. Highly non-local because every single guy talks to every other guy. And this is very different from Ising model, or two-state POTS model where we have nearest neighbor interaction. So this type of Hamiltonian defines a lattice model which is very, very non-local, but that's very good because we're expecting this invariant to be interesting invariant of a three manifold capturing global properties, and that's actually good. So anyway, that's what Hamiltonian is. Otherwise, it has very standard structure. It's bilinear or quadratic in this lattice variables. So then the only thing I have to tell you is what this capital F is. So what this function really is. And we can say that generating series over n of S I comma n, where I labels the vertex. By generating function, I mean that I take all of these coefficients and arrange them with z to the n, where z is a formal parameter. So this has to be symmetric expansion of z minus 1 over z to the 2 minus degree of I, expanded, you take expansion at z equals 0. In other words, you expand on positive powers of z. So if you have, I don't know, Mathematica, you do series at z equals 0, plus same thing, z minus 1 over z, 2 to the degree 2 minus degree of I, and you take expansion at z equals infinity. So that means you're expanded to negative powers, and you just average out. So we'll have already seen this before. So when I pointed out that this complicated looking integral can be rewritten in a more compact form, remember each vertex was basically given this sort of x minus 1 over x to the 2 minus degree weight, and that's exactly what it is. So the proof of this lemma is fairly simple, but I'll put it on the board, that what you can do is, in the integral that we had before, expand everything in this variables xi that we had. So it's a big thing. What you're going to end up is essentially with these coefficients, because you have to expand it in x and x inverse and xi's for every vertex. But then it's easy to compute convolution with the theta function, because so proof of this lemma, and I'll just give you the idea. So the basic idea is that you take this integral by residues, essentially. It's very simple. And you expand the integrand in xi's, but then the moment you encounter, for example, integral over dxi over xi, and here you have xi to some power m, and then theta function is something quadratic. So it involves sum over n in integers, x to the n, q to the n squared with some coefficient. So now we can actually take this integral. It's very straightforward. What it does, it tries to find values of m and n which are equal up to sign. So in other words, m plus n has to be 0. So basically what it spits out is q to the number times m squared, right? That's all there is. So that's actually what's going on. And that's why in this Mathematica file that I showed you, there was never ever an integration. It was already done for us. So this formula is much more straightforward way of rewriting the complicated looking integral. The integral came from integrating over holonomies, if you think about the Self-Citron-Simons or some physics nonsense, but it's actually not an integral. It's a sum, so that's the small lemma, yeah.
So this lemma just replaces the integral, we'd still have that Q or symbol.
Yeah, exactly, so you can, yeah, depending on taste, I never know what. Yeah, some people prefer keep it, it's actually good and it will be useful for us soon. Some people prefer to drop it because it's the same for all manifold, but then we have to remember that it actually should be there. We keep it. In fact, I do prefer to keep it, so following your suggestion, I'll do this.
I kind of would have expected the Hamiltonian to have like two terms, like electric and magnetic, or like kinetic and like potential or something. Is there any particular reason why we do have one term?
I don't know, that's a good question. I mean, in Chern-Simons, this quadratic structure reflects the fact that you have ADA, Chern-Simons functional, so it kind of starts with something quadratic. And you can think of this ends as contracting duals of some colonies, and that's not good.
So if I was like doing like
I don't-
Chern-Simons plus like the B cubed thing Pavel mentioned, maybe.
Good news is that, and that's why this is simple enough that, yeah, there is no, yeah, I would also imagine something cubic or more complicated, but good news is that it can be written this form again. Why conceptually, I actually don't know.
Maybe because the foundation is Chern-Simons.
Maybe, yeah, exactly. So that's another good problem. In fact, very good suggestion. Yeah, combining both of your questions, why? So or explain the structure and then maybe yeah, think about the HPs. So that's a very good. But it's I would say it's a research problem. I don't have an answer to it. But I'm about to answer your other question. So finally. Meanwhile, any other questions, comments? Yeah, well, this is a sketch of the proof or main idea for it. You can complete it. It's fairly straightforward. So this basically replaces the definition by definition as a sum, not as an. This is much easier. Right. So then you asked quite rightly earlier the following question. So clearly here all these choices were made. They look very esoteric, especially if we see them for the first time. So and they're obviously very crucial for this invariance under turbulence, which is important. Otherwise, we shouldn't even be talking about it. So very recently, so this is going to be a theorem. Ross Ahmedchev. Peter Johnson. And Slava Kruskal. And there are some other works, but I also want to mention recent work by Alison Moore and Nicola Taraska. Ask the following question, which is essentially the same question that you asked earlier. Can we, now that we have an example of such a thing, try to find other candidates for this F, keeping the rest the same, such that we have invariance under turbulence. So this is a very well posed question because we can write general ansatz or no assumption on this F and derive what equation they have to satisfy. So yeah.
So now I'm using V in this lemma.
Exactly. So that's another reason I would suggest going through the proof because you can restore the spin C structure dependence. You're absolutely right. So it should be on the left and on the right as well. So I'll leave it as an exercise to trace it back. Since I gave method how to convert integral, which did have everything precise, to the sum, that will be incentive to derive the spin C structure dependence. So this is actually a good official homework. Yeah, complete the proof. Complete the proof. of this lemma. And as a result, see how B enters. Yeah, so these fellows, they did assume that there is dependence on spin C structure. They assumed this general form of the ansatz, and they found that invariants. So basically, they found that there are infinitely many generalizations which is very cool. Because at first I would, if I were asked 2 years ago before any of this work was done, I would say that's probably pretty much the only one. Even finding this, I told you was super hard and so on and so forth, technical. Yeah.
You say infinite, should I think about like a discrete family or a continuous?
Yeah, I'm about to clarify this to the extent to answer a question, but maybe not to the full level of detail. Yeah, so originally I would expect that probably this is the only one. Maybe there is another version where you replace, I don't know, something like Q by Q inverse or a simple thing. But they actually managed to, they did a nice job of taking this general form and asking what do these Fs labeled by two things require to satisfy in order to have invariance under Kirby loops. So basically, in other words, in physics language, using like complex transaminds, one would ask how many non-compact TQFTs we have. Because usual transaminds that are greater and so on, they're compact, they're nice because their state spaces are finite. So here, this infinite sum over n is reflecting the fact that state spaces in this series are infinite dimensional. That's the difficulty in some sense. You need to regularize them. And they found that there are infinitely many. So that's very cool. We have infinitely many new invariants. And moreover, they wrote very specific equation for this F. So they said that all these generalizations are basically in one-to-one bijection with so-called admissible Fs. That's their term that they introduced. They, of course, have the right because they are the ones who worked out the theorem. Admissible functions F. And this admissible means that they satisfy a simple recursion relation which basically comes from demanding that it's invariant under Kirby modes. I'm not going to write recursion relation. It's a linear relation. It's not super complicated. It's something like F minus another F equals 0. That's a schematic form of it. So a bit different indices, shifted, some powers and whatnot. But the point is there are infinitely many solutions. So you can provide, I mean, it's a function that depends on two indices like our fellow. And if you fix some boundary condition, which can be like functional set of degrees of freedom over integer, you basically get the rest of it by recursion relation. So actually there are lots of things. So another obvious problem, which is a research problem, is to dive deeper and understand the meaning of this non-compact TQFTs, what they have. I mean, for example, I gave you a theorem earlier today that by taking radial limits, one can recover familiar non-semi-simple invariants such as ADO, CGP, and even Ricci-Tichon-Drive invariants, which are semi-simple. Natural question is, what happens here? So what we recover something else? I mean, there are so many new things. So where do they belong? We don't know. So that's a very
Sorry, just a quick question. When you say TQFT, do you mean they actually extend to like cohorted functions from cohortism category?
By TQFT, I mean in written sense, in a ORT sense, the most boring, where it just behaves well with respect to cutting and gluing. So I don't mean to say anything in terms of extended TQFTs, but it's all of this behave well in a sense you can cut and glue. Yeah, 3 manifolds along 2 manifolds. And I think that's actually another question which I don't remember off the top of my head. As I mentioned earlier, I personally care about integrality of coefficients. So we have a chance to categorify whatever that means. I think many of these are assume, I mean, there is a high subset here which gives integer coefficients, but I don't remember off the top of my head. I think it's something about setting up this recursion relation. Any other questions? So another thing that they do in this work, maybe I should also point out. I mentioned that there is this dependence on spin C structure, which was somewhat mysterious, and it's was a surprise, at least to me, because we're trying to find non-perturbative completion of complex transassignments, and suddenly we get with spin C dependent building blocks. Doesn't sound too cool, but again, now it's accepted. But they found another interesting connection. So they find connection. So maybe a remark here is that they also find a relation to figure theory, or more precisely Nemet's formulation of that, which is called lattice homology. Lattice homology of M3 or M gamma. So as the name suggests, this is a homological invariant of three manifolds. This is something that categorifies derived torsion or Seiberg-Witten invariants of three manifolds, and both derived torsion and Seiberg-Witten invariants are famously depend on spin C structures. So in my mind, a lot of demystification of spin C structures came from this line of work. And I like it also because if you're trying to build categorification of what I'm telling you about, this is probably the starting point. So there are also many ingredients that I think would be useful for future development. So there is a nice next theorem. So this is by Miranda Chang, Boris Fagan, and a large team, which says that for gamma of the form which has one trivalent vertex and as many vertices of valency 2 or 1, so it could be this or this. The feature is that we discussed gamma Q. Remember, it has the form Q to the delta. In fact, well, I'll write this B. There is a collection of such C0 plus C1 times Q plus C2 times Q squared plus dot dot dot. So this already looks like a character of two-dimensional conformal field theory or vertex algebra. Again, if you know this physics motivation that I mentioned, it's not a surprise, perhaps. But the statement is that this actually equals the character of logarithmic vertex algebra, known, which of course depends on a three manifold. So it's a function of your M gamma, if you wish, which is called 1, p singlet log VOA, where p is an integer. And I'm not going to give a general answer what p is, But Breeze-born spheres that we already saw earlier, they fit into this family. In particular, P equals P1 times P2 times P3 for Breeze-born spheres sigma P1, P2, P3, and there is an explicit formula that generalizes into two other graphs of this type. So this is very cool. Again, to me, this was a surprise. I had no idea what logarithmic vertex algebras are. They are not really my cup of tea at all. So I think it's okay. And even people like Sergei, forgive me if I say this, I didn't care. But it happened that the answer is a character for this graphs. So one just has to accept it, and it's pretty cool. It's interesting because logarithmic vertex algebras are hot subject these days for people who try to generalize vertex algebras. So vertex algebras, as canonized by Borchards and Polsky, many others, is a traditional subject. We know what they are. So once after 40 years, we exhausted that branch of quantum algebra, many people now move on to generalizations. And generalizations include this thing, logarithmic, which basically means non-semi-simple. And in fact, even in previous lecture earlier today, already I showed something logarithmic and non-semi-simple. And the cool thing about these algebras is that they're related via characteristic correspondence to non-semi-simple either quantum group representations or various categories and so on, or TQFTs if you wish. So in particular, this ADO and CGP invariants that I showed you earlier today are examples of this, and they fit into this story. But the relation to vertex algebras is not very, this points to a completely new relation to vertex algebras. Usual one is something that I showed you in the first lecture, that you have some TQFT in 3 dimensions, and then you try to analyze what's the space of states of this TQFT is, and you find that, oh, by the way, it also happens to be the space of conformal blocks of your work BOA or CFT, and that's a usual story. That's like 40 years old. This is something completely new. And it's completely new, and it didn't have a chance to be done before because we never had invariants of 3 manifolds which take values or have the form of the Q series. Because we always worked in quantum world at roots of unity. So we had no chance of writing anything like this. So therefore, this is completely new connection to vertex algebras. It's not of this old paradigm, and it can be confusing, but for new developments, this is something exciting. There is an obvious conjecture, which usually goes by the name of 3D modularity, in part because modularity of these objects is also very interesting, and it's closely connected to the fact that they're not fully modular, so that's why it's not usual VOA, it's a logarithmic VOA. So conjecture that this same thing is also true for all 3 manifolds. Okay. So this is quite useful because you can take your favorite graph, even it doesn't have to be super complicated, even this one, which has, for example, 2 high valency vertices, you can ask, okay, what kind of vertex algebra should be associated with this logarithmic theory? Even before we go to all kinds of complicated 3 manifolds given by surgeries on hyperbolic knots and so on, which is something we may want to do tomorrow, even in this territory of graphs, you can ask, do I know logarithmic vertex algebras labeled by graphs? And the answer is sort of, not really. So this is something new and pretty cool because you can associate a natural vertex algebra to a graph. We have bilinear form, which we call B. So we have a lattice, and there is a notion of lattice VOA. So in fact, one can try to construct this logarithmic VOAs out of much more natural lattice vertex algebras in the setup. And again, this is some ongoing program that I'm only tangentially know or involved in. But it's interesting in its own right because in this logarithmic world, the main challenge is to construct many new examples to understand what's going on, to learn about this vertex algebras, because this log relaxation of usual conditions is something that, again, basically cutting edge research. And thinking about it this way provides like a factory of log VOA, so we can learn their properties. And this is something I'm going to continue with tomorrow. This is one of the surprising facts that many people know. Okay, I'm going to stop here and take questions. Questions?
Is there a nice explanation along those lines of what you would assign to a disjoint union of corollas?
To a disjoint union of.
So like you said, for like if I have a single corolla, then this invariant should give me like the character of a.
Oh, you mean disjoint union?
Yeah, I have like two of these ones.
Well, I would expect that it's just a product. So if it's completely disconnected, it's very much like having, I don't know, TQFT evaluated on three manifold, which has two connected pieces. So yeah, that would be just a product. The only question then will be like normalization, which normalization we prefer or care about, but yeah, I would say it's multiplicative under disjoint union.
I was wondering, you had you mentioned that out of this graph, you extract a bilinear form, and then associated with this bilinear form, you have a VOA. Now, my understanding, so are you saying you can get log DOAs out of bilinear forms as well? I thought these sort of things are.
That's what the people like Fagan and others are doing these days, largely motivated by this. We can associate to bilinear form or a lattice, meaning lattice with a periodic form, normal DOA, not logarithmic, normal, I mean traditional from textbooks by, I don't know, Gukov and so on. So that wouldn't be logarithmic, but what people like Fagan and others do, they find some so-called screening operators. This is actually maybe interesting from BV perspective. So they find operators that are called screening operators. So this log VOA, for instance, this particular one sits inside lattice VOA. So that's a normal VOA over CFT. So here they find some operator S, which is called screening, such that S squared is 0 or something that we don't care about. And normal thing, which exists in every subject in math and also in vertex algebra, is to take cohomology of that. So that's a well-defined procedure. So that will give actually nice vertex algebra if you start applying this. But the trick they use is they say, okay, let's not take cohomology, but take kernel of S and not mod out by image of S. So that's kind of slightly legal thing. And because of that, we land in the world of these logs. So their construction, which many people these days call Fagan-Tipunin construction, is to take kernel of S on this like lattice theory. And again, I don't know, I mean, now there is an industry trying to apply to construct all this graph log theories in this way, and I don't know to what extent that's complete or.
The second name you said, Fagan.
Tipunin. So this is this sort of construction. It actually goes back to Felder because, so Felder had in old days, which is I guess late 80s, early 90s, realization of minimal models by taking cohomology with respect to screenings and introduced this what we now call Felder complexes and so on. And this is improvement on that. So this is Fagan-Tipunin. Was
In vector, is it hoped for all three manifolds or just the plumbed ones that we have these graph? Okay, and then.
If I have time, probably I'll have to sacrifice something tomorrow. There is a generalization of all of this beyond plumbed, and therefore there is conjecture is for all. There is no con, for example. I actually have no idea how to check it. But tomorrow I'll try to explain a feature that also comes from this story that's much more concrete. By checking it, I mean, how do I know if something is a character or not? Especially if it's not modular, right? If it fails normal modularity analysis, then it should. So one task could be to ask, what's the growth of these coefficients? And this is something that I'll try to explain tomorrow. It's much more pedestrian, much more centric. And this is something that even without knowledge of VOA, we can just go and test for every manifold, even of this computational device. I also want to maybe make one remark that I know now we are, especially with my digression into physics, starting to spread thin and go on different tangent directions. It's all cool, and there are many interesting things like Kazhdan-Lustig here and so on. But what I want to emphasize is that this is super computable. So to me, main ingredient here is that you can take pretty much any reasonable manifold obtained by Sergei or not up to 10 crossings and quickly get an answer within seconds. So if not for this, I probably would not be lecturing about it here. So everything that I'm saying can be extremely practical, tangible, and it's not just pie in the sky.
You had written before and you raised it, an arrow between the logarithmic VOAs to non-semi-simple TQFTs via Kazhdan-Lustig was the arrow?
Yes.
Okay, so how does that?
Four categories, that's probably more for quantum groups.
Okay, so but you think of those as being associated to TQFTs?
Yes, yeah. So yeah, basically it's like a three-step or two-step construction where you can associate, you extract from log VOA the category, then you ask, have I seen this category, for example, in quantum groups? And another question is, can I, using this category as input in say Thrive-like construction, produce it?
Yeah, I was gonna ask because I'm used to like seeing these log VOAs coming from like logarithmic CFTs, which maybe then you're trying to think about TQFTs related to those. And yeah, I haven't really seen the non-semi-simple constructions from, or like, I know there's work connecting logarithmic VOAs with quantum groups, but it's still not like modular or anything like this. It's very much graded or.
Yeah. So yeah, that's exactly the point. These are not modular characters. So even asking what is like MTC, M stands for modular. So we have to write S&T matrices, what's the analog of it, and so on. It's confusing. So tomorrow I'll try to show actually how this gives very concrete handle on that. And it very quickly goes beyond something that we know and love. So in log VOAs or log CFTs, we have three beaten families that everybody loves, singlet, triplet, and like symplectic fermions. So this gives you like infinite generalization. It says that for any graph, there should be such. So it's like way more than we can imagine in non-semi-simple logarithms. Again, I'm not that kind of person, but it's good that it's a factory of such things.
I'm sure there are more questions, but maybe we'll wait here for today. Sergei again.